So let's look at few places where you do actually see advanced packaging. So uh, I have 5 examples where you do see advanced packaging in your iPhone. So you can see it in your microprocessor, you can see it in your flash memory cell, in your camera, in your display. So I'll just describe to you those different places. But if you look at your iPhone, your whole computer, which used to be that big, is now in that small PCB. And I would say most of it has to do with packaging. Some of it has to do with Moore's law, but a lot of it has to do with packaging. So let's look at the first place. This is something I just touched upon earlier as well, but the microprocessor of your in all your smartphones is a package on package, which what it means is that there are these. The bottom layer is typically your microprocessor or your system on chip, and the top two layer and the two chips that you see on the top on that SEM image are these DRAMs which are placed on top of this microprocessor. And these top two chips are already made into a package, and this microprocessor below is already into a package. It's just that these two packages are placed on top of each other. And the reason here is more from a form factor reduction point of view. It does not give you too much performance benefit if you just place a package on top of the package. But since that your smartphone is so constrained for space, people still do it. And this is one of the reasons why Apple still gets its microprocessor from Samsung, because Samsung is one of the companies which is vertically integrated, that they can make the processor for Apple. They can also make the memory, the DRAM chip, and they can package it together and sell it as a package instead of selling those chips individually. And that's trivia of information. So you could place these two chips in two different places. There's essentially two chips, so you could only place them. Either you place the DRAM on the top, or you place the microprocessor on the top. And so there's one implementation. So which of these implementation is better for your thermal management perspective? Okay. And the reason being? Yeah, so most of your heat would be generated by this guy. And so if you place it on the top, you can have a heat sink on the top that can take that heat out. If you place it like this, not only is bad for taking the heat out, but now you're doing even worse. You're heating up your DRAM. So if you heat up your DRAM, the retention of your DRAM cell will go down. So it's pretty bad from a heat management perspective. But is it better from an I/O perspective? And the reason is that most of your I/Os or most of your input-output connections, they are going to your microprocessor. So from an I/O perspective, if you did this implementation, you could have this chip, flip chip bonded, and you could have most of your I/Os coming from your PCB. And on the other hand, if you did it like this, you'll have to have these wire bonds which will take all these I/Os from your PCB to your microprocessor. So this is the reason why they do it this way. So we saw that over here the microprocessor is placed at the bottom because you can flip it and you could have most of your I/Os coming from your PCB going directly to your microprocessor. But it's a really shabby implementation from a thermal management perspective, because this will heat up, and then in turn that will heat up your DRAM. If you know a better implementation, you can tout it out. But essentially there's not much you can do there. Only two chips, and you can only place them two ways. So the other place where you see this advanced packaging is in your flash memory. So uh, I showed you one picture when we were talking about flash, that if you open up that flash memory chip, you'll see that one package could have up to 32 of these dies, each die being 8 gigabit in capacity. So you can now store 128 gigabyte in one single chip, and these things are placed in this double domino fashion. So if you even place them in a domino fashion, that will take up too much area. So it's like a double domino. So there's one domino, and then there's another domino on the bottom, and then there's this third domino below it. And each of these dominoes is placed, and then you wire bond to that domino. Then you place the other domino, and then you wire bond to that other domino. And then you place this third domino, and then you have these wire bonds to that third domino. And then many a times you have your controller chip on the top. So your controller is placed on the top of these 32 chips, and you'll see that controller communicating with each of these chips. So now you have to again figure out a way for that controller to connect to each of these chips as well. So it's when you look at these chips, sometimes it feels unbelievable, that it's almost some work by a superhero or something. Doesn't look like something that would work in actual life, but it does. And wire bond technology is very pervasively used, not only just for flash chips, but it's used for placing this package on package, and it has a lot of still has a lot of steam left into it. It's not going away anytime soon. And these wire bonds used to be gold wires before. More recently, if you have seen the gold prices, they have gone up by more than a few times in the last few years. So people have switched to copper gold wires, but that comes with some trade-offs as well. So the third place you see advanced packaging being used in your phone is in your camera. And if you're not aware about your image sensor, so there are two types of image sensor. One is a CCD sensor, which is these charge coupled capacitor devices, and then there's a CMOS sensor where each of those sensor is connected by a CMOS circuitry. And what has happened is CCD used to be used very prevalent again up till 2000, but nowadays it's almost everything is switching to CMOS. And even within CMOS, things are switching from a front side illumination to a back side illumination. And these are so it's a pretty big market to play in. It's around $5 billion annual market. And the companies which were smart enough to figure out that backside illumination will be big, like company like OmniVision, Sony, they are gaining more and more relevance because this technology in your CMOS image sensor is changing from front side to back side illumination. So what do I mean by front side or back side illumination? So there are two ways you can illuminate your image sensor, or you can get light into your image sensor. One is that you have your image sensor, which is in your silicon over here, and then you have these different levels of metal. So you have what you typically call as back end of the line, or your interconnects, and these interconnects are placed on top of my silicon. And this is the way it used to be done. You need these interconnects to run the circuitry, connect all these individual cells, and this is the way it was done traditionally. And pixel size used to be, this was fine when your pixel size used to be 20 micron or 30 micron, because the percentage of that metal wiring was a very small fraction of your overall chip layout. But now your pixel size, if you have your iPhone 5, which has an 8 megapixel camera, those are typically around between 1 micron to 1.5 micron in each dimension. And if you have that and you have multiple of these wirings, a lot of your light, a lot of your incoming photons will essentially get reflected back from striking these metal levels, or they'll get diffracted, or they'll get scattered, neither of which is good for your overall camera performance. And this especially hurts you when you have low light. So when you have less number of incoming photons and you scatter or reject them back, that especially hurts your low light performance of your camera. So the most recent thing which has happened in CMOS image sensor is people have flipped this chip around and they have moved to this backside illumination. So what you have is your image sensor just directly faces your lens, and all your metal wiring is at the back of that chip. So it does not interfere with your incoming light. So here's the image of your iPhone 4. So this is the X-ray image looking into your iPhone 4 camera, and that used to have a front side illumination. So you can see these metal wirings on the top, and there are lenses on the top as well. And this changed substantially when people moved to, it should be iPhone 4S, I apologize. So when people move to 4S or iPhone 5, you can see this metal wiring is at the back, and your image sensor, the part which is receiving the light, that's facing your lens directly. And iPhone 4S has 5 of these lenses on the top, and so you have nothing which is interfering between that light coming from your lens and hitting your image sensor. And this is one of the reasons you get much better photos with BSI technology or backside illumination. So how is this enabled? So the process flow is relatively simple. All you do is instead of having a bulk wafer, you start from a SOI wafer, and you make your image sensor. You make those multiple levels of these interconnects, and then when you are done making that, when you are done essentially making a FSI kind of sensor, you bond it to another piece of silicon on the top, flip it around, and remove that initial silicon wafer. So now you're left with this silicon facing the top. And then you put your anti-reflective coatings, you put color filters, micro lens, and put a glass on the top. And then you thin down this handle wafer. And typically, so I'll talk about this. You make these TSV or these holes in this handle wafers. And typically, your image processor is placed directly or bonded directly at the back of your CMOS image sensor as well. So there's quite an amount of processing and process technology, especially when you come over here, which is involved and which enables your CMOS image sensors in your iPhone. The final thing that I want to talk about, which involves advanced packaging in your iPhones, is your display. I want to give you some flavor here, but we'll talk about this in much more detail next week when we talk about displays. So, this is 5 versus 4. So there's a 1.7 mm reduction in your overall height of your phone, right? And 1 mm of that comes from the reduction in the total volume of your, not the total volume, the total height of your display. And what's happened in the field of display is that all these touch devices, you have your LCD panel, which is at the bottom, and then you have a touch screen, which used to be a separate part. So how this touch screen was made was it was an intersection of these two conducting electrodes, and these conducting electrodes these are called as transparent conducting electrodes, and they are made of material like ITO, which stands for indium tin oxide, or material like zinc oxide. So these are these two interconnecting, not interconnecting, intertwining array of these conducting electrodes. And so if you press your finger on it, the capacitance between these two changes, and it detects that and senses your touch input. So traditionally, all the way from the first iPhone in 2007 to 2012, this touch screen always used to be a separate layer. Initially, there was air in here. They got rid of the air, and then they started to laminate the touch screen directly on top of your LCD. And on the top, always there's this cover glass. It's also called Gorilla Glass because it's made by only one company which makes this Gorilla Glass for all your touch devices. Does anybody know that company? Cree. Cree is a LED company. Yeah, Corning. So it's made by Corning, and it's made by a plant in Kentucky. So that's the display at least made in US. No, the cover glass is made by Corning in US. So what's very interesting thing is happening on this touch screen. So this touch screen, what it does is, first of all, it interferes with your light, which is coming out of your LCD. So it causes a 10% reduction in your overall brightness. Another thing is ITO it's turned out to be, as more and more people have started using smartphones and iPads and tablets, the demand for ITO has gone up real fast. So it has become a very expensive material. And remember, we talked about that touch screen being $40. So this ITO roughly costs around $1 per square inch just for that coating. So if you have your iPad size display, it would be 15-20 bucks just for this ITO coating. So first of all, it degrades your performance of the brightness of your display. It costs quite a lot. So people what they have done is they are trying to get rid of this touch panel, and there are two different approaches you can take. You can either integrate that touch, those electrodes which enable your capacitive sensing into your LCD, and that's called an in-cell approach. Or you can take that this capacitive sensing and move it into your glass, and that's called the on-cell approach. And Samsung and Apple have taken different approaches to it. So Apple does it in an in-cell way, where what they have done is they have taken that touch screen and moved it into your LCD. Samsung, which uses a OLED-based display, it does an on-cell approach where you have that touch sensor integrated into your glass. And we'll talk more about that next week when we talk about displays. But using that in-cell technology allows you to increase your brightness by 10%. So there are 4 companies which used to make displays for iPhone or these smartphones, and 2 of them adopted this in-cell technology, so they are still in business. The other ones, they don't get any orders. So these are the 4 places where there's MEMS chips which use advanced packaging as well. But we are not talking about MEMS in this class, but the main purpose of packaging in MEMS is to provide a hermetic seal. That is, you have these cantilevers and gyroscope, and you want to seal them off from atmosphere. And more recently, what has happened is whatever the learning that these companies have gained over packaging your iPhone, so when you open their other products nowadays, you see very similar kind of packaging, that all those things that you have learned from making an iPhone, those are enabling things like these MacBook Air, or even the newer MacBooks that were announced last week. These are essentially learnings from packaging, uh, learned from packaging your iPhone, and then you're applying it across. So you see this conversions, or technologies coming together, and that's what enabling all these other thin form factors, even where places where you don't expect them that much.